This is the Unit 12 review. I've got all of the answers sort of filled in here in blue, and I'll just probably emphasize on the main points that I think you need to know from this. Otherwise, you can kind of just read through it and figure those things out for yourself, and then ask me if you have any questions about those sorts of things. So this first section here is on solids and liquids and gases. Something to keep in mind here that's a little bit confusing is there are two ways that we can kind of interpret these. You can be comparing, say, for instance, two things that are at room temperature. One is a solid and one is a liquid, in which case you're kind of talking about different intermolecular forces there. The one that's a solid would have stronger intermolecular forces than the one that's a liquid. However, you could also be comparing two phases or two states of matter of the same substance, say a solid versus a liquid, for instance, solid water versus liquid water. And it gets a little bit confusing when we're making those two different distinctions. So try and keep these things straight, because some of these things only apply if we're comparing a solid to a liquid of the same material, and some of them apply when we're talking about a solid and a liquid both at the same temperature. So yeah, I'll kind of try and work through that. So solids being organized, that's always true. Slow-moving particles, that has to do with temperature, generally speaking. So that would be one where we're talking about like things being a solid when they're cold. Low energy, similarly, the same thing. Definite shape, that's all solids. Strong attractive forces, that's when we're talking about things at room temperature, for instance. Like things at room temperature would have strong attractive forces if they're a solid. Liquids, it says particles are going faster and they can move around more. So this is talking like if we're saying two samples of the same substance at different temperatures, when you're going from a solid to a liquid to a gas, you're changing phase there. Particles are going faster in a liquid than they are in a solid if you're talking about the same substance. In liquids, this is generally speaking, they're going to take on that shape of the container that they're in. They're going to fill the bottom. Gases, particles very spread out. That's true for all gases. Fast moving, this would be if we are comparing different states of the same substance. So gases are faster moving than liquids if we're talking about the same substance. High energy, also talking about if we have the same substance there. All gases take on the shape of their container, so they fill it completely. So as I said, I know that's a little bit confusing because we have those two different ways that we talk about solids and liquids and gases, but hopefully that should make sense, and they shouldn't come up in any terribly tricky ways when they come up in the exam. The one thing that I would say here is that you should know that if a solid and a liquid are at the same temperature, let's say they're both at 45 degrees Celsius, that means they have the same kinetic energy because temperature is directly related to kinetic energy. Temperature means average kinetic energy. Question number 2, you can kind of just read through there. I've said that a bunch of times, hopefully in class, so just make sure that you have that dedicated to memory. Also, for question number 3 here, make sure you can identify the different types of forces in a substance. If something has really strong intermolecular forces, it's more likely to be a solid at room temperature. If something has really weak intermolecular forces, it's likely to be a gas at room temperature, things like that. And then know when each one would apply. So for instance, if we have polar molecules, it's always dipole-dipole. Everything has London dispersion forces, and hydrogen bonding is only involved with substances that have O, N, or F in them. Question number 4 here is talking about, again, sort of intermolecular forces and why some things have one state of matter and other things have another state of matter. So we're saying here at room temperature we've got water and we've got methane, and water is a liquid whereas methane is a gas. And so it says, you know, okay, thinking about this, why is this the case? Which one has a larger or a higher boiling point? And what's going on here is that water has hydrogen bonding, and in fact, water has 2 hydrogen bonds. It's got one here, hydrogen to oxygen, and it's got another one here, hydrogen to oxygen. And so that makes it incredibly, incredibly polar. Methane here is a small molecule. It's nonpolar. The intermolecular forces are very weak, so it tends to be a gas at room temperature. And that generally should make sense because since the particles aren't very attracted to each other, it's very easy to spread them out. So making it a gas is not too hard. Question 5 here, talking about boiling a pot of water. It says you stick it on the stove. Even if you have kind of cold water, you put it on the stove. It doesn't take too long for it to start boiling, like maybe 5 or 10 minutes. But then you could boil it for hours if it was a big enough pot, and it just wouldn't boil out. And so the question is, why is that? Well, if you look at the heating curve for water, or the heat of vaporization, 2,256 joules per gram, it takes a lot of energy to boil water. The heat of vaporization is high, and the reason is for a couple reasons here. We said going from a liquid to a gas, heat of vaporization, it's pulling the particles completely apart, very far away from one another. And so you have to overcome the intermolecular forces. Also, when you boil something, you're overcoming the atmospheric pressure. And the last thing here is water is just particularly high for its heat of vaporization because that attraction is so strong. You have to overcome the really, really strong attraction. Question number 6 describes the process of something going from being a solid that's below the melting point all the way up to a gas that's above the boiling point. So this actually is a really, really important question that you understand because a lot of the concepts I ask are related to this. So what we start with is a solid, and it's below its melting point. So the particles are moving really, really slowly, just vibrating in place. You start to heat it up. The particles are vibrating faster and faster. Eventually they get moving so fast that they can kind of pull away from each other a little bit and flow around, which is why you get the property of liquid where it's all kind of staying in one glob, but it can move around a bit because the particles are kind of separated just a little bit, enough so that they can move. Then you heat them up more and more, and so they get faster and faster. And eventually, as that liquid heats up to the boiling point, they're going so fast that they can pull apart completely into gas form. And then if you've got all gas, if all the particles are pulled apart and you continue to heat it, then you're just adding more and more kinetic energy there, and the particles continue to speed up and move faster. On here to the back of the page, we've got this question here. It says, if you increase the atmospheric pressure, I've asked this in a few different ways, but I'm asking how it affects cooking time. So what happens here is if we're increasing atmospheric pressure, what's happening is there's more bombardment sort of coming down from the atmosphere onto a liquid. So as it's trying to boil, if there's more particles hitting harder into the surface of the liquid, it's harder for it to boil, and so we have to get it up to a higher temperature for it to boil. If that's the case, then things would cook faster. The opposite case being what we had talked about, where in Colorado air pressure is very low, so things boil easily at a low temperature, and then it takes longer to cook them because they're boiling so easily at that low temperature. So that's how that works. Looking over here, number 8, this requires that you understand this heating curve here, and so I'll kind of demonstrate the things here. So all of these sloped regions here, E and C and A, all of those, the temperature is changing. So kinetic energy is changing. During the flat periods, D and B, temperature is not changing, so all that energy that you're putting in is going to separating the particles, so that has to be potential energy because temperature is not increasing, so we know kinetic energy is not increasing. Knowing that D is melting, whereas B is vaporization is important. Other than that, just go through that set of problems on heating curves, and I think that a lot of this sort of thing, you can work that out. You can try and figure out what each of these sections represents, but there will be a couple of these on the test, so try not to get confused with that. This E down here says which temperature represents the condensation point. Condensation is going from a gas to a liquid, so that's going to be here, going from a gas to a liquid. And then the next one says the freezing point. Freezing point is going from a liquid to a solid, so that's D. So you can just pull those temperatures directly off. And then we can tell this one's not water because melts here at 60 degrees and it's got a boiling temperature of 80 degrees. Page number 3 here gets into talking about the different types of problems that we have here. Questions 1 through 3 on this section are all about phase change. Question 4 and 5 are using the heating curves. So I'll go ahead and do all these problems so that you can see what these are like. This should give you a pretty good indication of the types of problems that are going to be on the exam. If you feel pretty strong with these, I think that you're pretty good to go. So question number 1 here is talking about, it says, what is the enthalpy change needed to convert 5.25 grams of methane gas into a liquid? So we're going from a gas into a liquid. And if that's the case, all right, this is the last page here on this review guide. All of these are math problems that you'll have to do. There are different sections here. The first 3 questions are all about heat of fusion, heat of vaporization, phase change, things like that. The bottom 2 questions are both heating curve problems, so this is a pretty good representation of what's actually going to be on the exam, so knowing how to do these problems will probably definitely help you. This first one here, what we're doing is it says we're converting 5.25 grams of methane gas into a liquid. So in this one, gas into a liquid, that's condensation, so we're using heat of vaporization. So we set up delta H equals m times heat of vaporization. This is methane. We're starting with 5.25 grams. We know that for every 1 gram that we have here, 480.6 joules of energy is released. Since this is an exothermic process, we've got 3 sig figs in the 5.25 grams, 4 sig figs in the negative 480.6. So our answer should have 3 sig figs. We round that. It's negative 2,520 joules. The next problem here, problem number 2, says how much energy is released when 100 grams of ethanol is frozen. So frozen is heat of fusion. Freezing is also exothermic, so this is going to be negative as well. This one says how much energy is released, and I'll kind of touch base on that at the end, how this one has a slightly different way of answering it, but it's not too bad. So we've got delta H equals mass times heat of fusion. Again, going between a solid and a liquid, or a liquid and a solid, is always heat of fusion. So 100.0, that's 4 sig figs, grams. This one, for every 1 gram, we have 99.85 joules released. Multiply those together, we get negative 9,985 joules. All right. Now this question said how many joules are released. I probably wouldn't do this to you on a test because it's a little bit too confusing. But negative 9,985 joules, that's the delta H. That's the change in enthalpy here. But if you're asking how much is released, the negative sign is implied in released. So we'd have 9,985 joules released. And as I said, that released implies the negative. Question 3 here says, what's the enthalpy change when 2,500 milliliters of water freezes? This one is kind of relies on the fact that you know that this is 2,500 grams because of the density of water. 1 gram is 1 milliliter. So if we're doing that, again, this is freezing. So we're using heat of fusion. Delta H equals mass times heat of fusion, which equals 2,500, 2 sig figs there, times the heat of fusion, which is going to be negative 334 for water. And 1 gram, this is, oops, sorry, that's just grams there, 2,500 grams, negative 334 joules. Multiply those together, we get negative 840,000 joules. 2 sig figs on that one. All right, on to this first heating curve problem. On this one, it says that we've got 1,000 grams of water at room temperature, which is 25 degrees. We're trying to heat them up to a liquid at 100 degrees Celsius, and I say no boiling occurs here. So we're starting out at 25, and we're going up to 100. This one is actually just a one-step process. We're just changing temperature here. So we're going through this very small part of this. The equation for that is Q equals mc delta T. As I said, only one step, which equals 1,000 grams times C for water, 4.184. Delta T for water is the 75. We multiply those things together, we get equals 313,800 joules. And remember, we're not following sig fig rules on this one, because the heating curve ones we don't. On the last problem here, it's another heating curve. This one says that we have 4.5 grams of steam at 400 degrees Celsius. We're cooling it to liquid water at 100 degrees Celsius. So here we're starting up really, really hot. We cool it down. We condense it to water at 100 degrees Celsius. So this one is just 2 steps. The first one, cooling down the steam. The second step, we're condensing it. So step number 1. Since we're cooling it down, it's Q equals mc delta T. M in this case is 4.5. C is 2.070 for steam. Delta T, negative 300, because it goes from 400 down to 100. We multiply those all by each other, we get negative 27,945. The next step is to condense it. So step 2, we've got delta H equals mass times heat of vaporization, which equals 4.5 times 2,256. We multiply those together, I get negative 10,152 joules. That was because this is negative, because condensing is an exothermic process. So there's just 2 steps here. We add them together, I get negative 38,097 joules. All right, that is that. So if you have any questions about this assignment, make sure that you come in and talk to me. Try and do it a little bit before the exam so it's not just crunching it in there at the last minute. But yeah, let me know.